Hi everyone, Dr. Burns here with one of our last lessons in Chapter 19, where we're going to be talking about calculating E cell for our different electrochemical reactions, our redox reactions, when we're away from our standard conditions. So we've talked about how to calculate this for standard conditions, so 1 molar, 298 Kelvin, 1 atm. But now we want to talk about non-standard conditions. When we're talking about non-standard conditions, we're mainly going to be focusing on different concentrations of our solutions, so away from 1 molar, and that's what we're going to be exploring more in depth here today. So we've talked about in previous chapters, mainly back in our thermochemistry chapters at the beginning of the semester, that when we're away from standard conditions, we have to calculate our values differently. So we've looked at that with delta G. We looked at it with delta G naught versus delta G. We said if it has that little naught symbol, then it's going to be standard. But if it does not, then it's non-standard, and we have to account for that differently. We have to offset that value by some amount that accounts for that non-standard condition. So the same is going to apply to our redox reactions, to our voltaic cells, and to our electrochemical reactions. And so we are going to explore a different way for calculating E cell. So when we have our E cell naught, okay, that's our standard condition. So we have E cell naught, we have that naught value, we're going to be looking at our standard conditions. We still have to use that E cell naught, we still have to use that standard E cell when we're calculating our non-standard conditions, but we have to account for the non-standard. So when we're looking at non-standard, we're just looking at E cell with no naught value. So this is saying that it's non-standard. So when we're away from standard conditions, the equation that we use to calculate E cell is called the Nernst equation. Okay? So the Nernst equation can be seen right here, where E cell, that's again away from standard conditions, is equal to E cell naught, our standard conditions, minus RT over N times F ln of Q. Some of these variables may look familiar to you from our previous discussions of equations earlier in this chapter, as well as in previous chapters, but let's just remind ourselves what those variables mean, okay? So we know that E cell and E cell naught, those are E cell values at standard and non-standard conditions. R is going to be our ideal gas constant. Okay. T is going to be our temperature. And we're always going to have our temperature in Kelvin. We then have N, which is in this case going to be our number of electrons transferred. I should say the number of moles of electrons transferred. And F is going to be our Faraday constant. We've looked at an equation earlier in this chapter when we were talking about the spontaneity of redox reactions that had all of these variables involved, except instead of using Q, we were using K. So the specific thing here is that we're using Q. Q means we are away from our equilibrium. Okay, if we're away from equilibrium, that's also our non-standard conditions. Now we've looked at this when we compared E cell naught to RT over NF ln of K. Okay, we've looked at it there. We also looked at log K as well, but we were looking at K. So here what we're doing instead is we're taking our standard condition value for E cell and we're offsetting it by our non-standard conditions. The second variable here, specifically in the Q, is where those non-standard conditions come in. So I said earlier that when we're looking at non-standard conditions here, we're looking at specifically different concentrations. So that would be different concentrations of our reactants and our products. So what we have to remember about Q is that Q is going to be equal to the concentration of our reactants over the concentration of our products. Now typically if we were at standard conditions, we would be at 1 molar for each of those values, so 1/1, so that wouldn't change anything. But if we're at non-standard conditions, those concentrations could be 0.1, or they could be 0.5, or they could be 2 molar, so they could be different concentrations. So we're offsetting our standard conditions by this variable here, this value that takes into account our non-standard concentrations. Other ways that we could be non-standard could also be in our temperature. Temperature could be non-standard, so we said standard temperature is 298 Kelvin. We could technically do these non-standard conditions at a different temperature and use this equation here, but our textbook doesn't go too deep into those different temperatures. We mainly look at different concentrations. But if you ever came across a problem where you weren't at 298 Kelvin, then you would have to use this this equation, the Nernst equation, because you would be away from your standard conditions. So just like our previous E-cell equation that we talked about when we were talking about spontaneity in reactions, we can simplify the Nernst equation due to our constants that we have. So R is a constant. We're going to see T as a constant, again, because we're typically not changing our temperature from 298. F is also a constant, so R, T, and F are going to be considered constants. Again, if you're away from that standard temperature, you can't use this simplification. So if you were to do a problem that was away from this temperature, you could not use this simplification. But for right now, we will assume that we're going to keep our temperature 298 Kelvin. So if we were to keep all of those constants, R, T, and F constant, this would be our simplified version of the Nernst equation. And this is what you're going to see available to you in your instructor resources. You technically have both, again, if you did have to use that first version with different temperatures, but you also have this version as well. So the variables that you need to be calculating are either going to be E-cell at non-standard, E-cell not at standard conditions, which we know how to calculate. This is going to be our reduction potential of our cathode minus our reduction potential of our anode. Okay, so our cathode minus our anode. We also need to figure out the number of moles of electrons that are transferred. So we'll have to look at our half reactions in order to do that. And then we need our Q. Before I do that, let's say from balanced half reactions. Let's just clarify that. And then we need to calculate our Q. So if we're at non-standard conditions, we're going to have different concentrations. So we need to calculate the ratio of our reactant concentration to our product concentration. Now, we've been looking at redox and electrochemical cells for a while, and we know that there's always going to be these solid components, a solid metal on either side of those reaction, or either side of the arrow in the reaction. So you have to remember that solids don't count towards Q, just like they don't count towards K, so we would ignore those. So these would specifically be the concentrations of the aqueous solutions. So when we're looking at specific problems, we ignore the solids when looking at Q. We have to look at the solids for the half reactions, but we ignore them when calculating Q, and we specifically look at our aqueous solutions in order to calculate Q. So these are the 4 variables that we are either going to have to calculate or will ultimately be calculating at the very end. So there are some steps that we have to do in between. So it's important to note that we have to calculate our value of Q. So again, let's look at an example of a reaction that allows us to see how Q is going to be set up, how we ignore those solids and everything, remind ourselves what Q is here, because it has been a while since we've looked at Q. So here I have the reaction of zinc solid plus copper ion in equilibrium with zinc ion and copper solid. Again, we typically see these as one directional, but because we're looking at Q and K, there is a slight equilibrium that's going back and forth between these reactions. Okay, but when I write the half reactions, we're just going to write a single arrow just to make it easier for us. So we do have to calculate a few values here. Now, In my problem that I've given you the E cell for standard conditions. Typically, you're not given this. You will have to calculate that first if you want to use it in the equation. So you need to write out your half reactions. It's also good to write out those half reactions so you know how many electrons are needed between the two reactions. They need to be balanced for electrons in both half reactions to ensure your N is correct. So here I have N is 2, so let's just double check that it is in fact 2 electrons that we need. So our first half reaction is going to be between zinc solid going to zinc ion. And then we also have copper ion, copper 2, going to copper solid. So those are our two half reactions. So zinc turned into zinc 2 plus, copper 2 plus turned into copper solid. So now we just need to balance for our electrons. So on my zinc, I have a 2 plus on this side of the reaction. So I need to add 2 electrons onto the other side. This side has a 2 plus. This side originally had a 0. So if I want to get these to be the same charge on either side to have charge balance, I have to add my electrons to the side that needs to get more negative. So that would be the product side. Okay. And then because I had my electrons on the product side in that first half reaction, my other electrons are going to go on the reactant side of my second. Now, this has a charge of 0, this has a charge of 2 plus, so I need those 2 electrons. So because I needed 2 electrons here and 2 electrons here, that's why my N over here is 2, because the number of electrons that were transferred were 2 electrons. I know we talked about this in class previously, but if for some reason we had a half reaction where it was one half reaction showed 1 electron and the other half reaction showed 2 electrons, you would have to multiply that first half reaction by 2 in order for those number of electrons to be equal to each other in the 2 half reactions, okay? They have to be equal. The number of electrons I lose has to equal the number of electrons I gain. We can't just be losing electrons to nothingness. They have to go somewhere. Okay, so because we have our 2 half reactions, we then know what's being oxidized and what's being reduced. Reduction, the electrons are on the reactant side, R and R. So here's my reduction, which is also my cathode. We remember reduction and cathode because R and C are both consonants, so those words go together. If the second reaction is our reduction, that means the first one is our oxidation. I have my electrons on the product side. Okay, so it's a product of the reaction. I lost those. So if this is my oxidation, then this is also my anode. I remember those words go together because A and O are both vowels, so they go together. So we need to know those 2 half reactions. We need to know our anode and our cathode in order to do our E cell knot calculation. So we would do cathode minus anode. And those values we get from the table, from our list of reduction potentials, and that's how we get the 1.10 volts. I believe we looked at this reaction back in class the other day. So we did see this calculation previously, but it's just cathode minus anode. So that's how we get our E cell knot. So right off the bat, we have to look at our 2 half reactions in order to get N, as well as to get E cell knot. Finally, we look at Q. So Q here, we're only taking into account what's aqueous. So we know that copper ions are aqueous and zinc ions are aqueous. We're going to ignore our zinc solid and our copper solid because solids don't contribute to the equilibrium or the Q calculation. We ignore them because they don't have a concentration. They're not an aqueous solution, so they don't have concentration, so we ignore them. So because we're doing reactants over products, products over reactants, oh my goodness, have I been writing that wrong the whole time? I probably have. Goodness gracious. Products over reactants. I apologize if I've been writing that wrong. There we go. We figured it out now. I'm sorry. I'll make sure to remedy that. So products over reactant concentrations. So we're going to have our zinc ion concentration in the product numerator and our copper ion concentration in the reactant denominator. Okay, so we're going to have products over reactants. So what we would need here for this specific problem is those specific concentrations. Okay, so when we're calculating with our Nernst equation, we can't just look at the concentrations that are given. There are a few other calculations we have to do, other equations we need to write in order to get the other variables for our reaction. Okay, but we're just building on what we've talked about in the past. So here I have the same problem, and now I give you those two concentrations. So my zinc ion concentration is 1.02, and my copper ion concentration is 0.55 molar. So again, I have my same equation here. E cell is equal to that 1.10 volts. That's our E cell naught, our standard conditions. 0.0257 volts. That's our simplified of all of our constants. And then we have our two electrons, 2 moles of electrons from our half reactions. And now we're going to do our natural log of our concentrations, our product over our reactant concentrations, now that I've got that written correctly. So our zinc ion concentration is 1.02, and our copper ion concentration is 0.55. So now we have all of these variables, we can go ahead and solve this problem. I personally like to go stepwise just to make sure I'm not missing anything. So I'm going to do the natural log of my ratio, 1.02 divided by 0.55, making sure that both of those values are in my parentheses. Okay, and then I'm going to multiply that by my 0.025 divided by 2, again making sure those are in parentheses together. Oops, I missed a 7. There we go, 257 divided by 2. So multiplied by that. And then I will do my 1.10 minus that answer. So we get an E cell at our non-standard conditions of 1.09 volts. So 2 decimal places to match our 2 decimal places with our other voltage. So we want to have these significant figures match our original E cell at at standard conditions. So what is this telling us? Well, it's saying that at standard conditions, I would expect my voltaic cell to have a voltage of 1.10 volts. That's if I had 1 molar concentrations for both reactants and products. Here, I'm now changing those concentrations. So now it's 1.02 and 0.55. So I'm decreasing one of the concentrations by almost half and increasing the other concentration very, very slightly. Okay, so what's happening is I'm offsetting the amount of voltage, the amount of electrons that can be either transferred or accepted in either half reaction. So again, that's what this variable is doing here. It's an offset to our standard conditions. So it's saying because I decreased that concentration of my copper ion, where I'm having the reaction or the reduction happening, that then decreases my voltage, so decreases the amount of electrons that are going across my electrochemical cell, so that wire that connects our 2 electrodes, our anode to the cathode, less electrons are now going through. They're going through less fast, a little bit slower, so that voltage is a little bit lower because there's less of a concentration of the copper ions available for the reduction to be happening. Okay, so because we decreased that reduction concentration, it then decreases that voltage. If we saw an increase in that reduction concentration, so if instead we doubled it, we would see that this concentration would go up, or this voltage would go up, because there's now more ions present for that reduction to be happening. Okay, so we can find these values to be very close to each other, or they can be very far from each other. It kind of depends on the concentration of the 2 reactants, or the concentration of all the reactants that we're looking at and products. So notice how these are kind of close to each other. Again, we weren't too far from our original values, so these values are then really close to each other. So it's a good way to check our work. As we say in all of these values that we see these relationships and these offsets, they're going to be close to one another. I'm not going to change my voltage by 2 or anything like that. So if we start at 1.10 for standard, my non-standard is going to be in the same realm. I shouldn't be seeing this jump up to like 2 volts or 3 volts at non-standard conditions. So they should be within range of each other. I'm not going to give a specific value because I don't want you to think, oh, if I'm off by this much, then it's wrong. It's like they should be close to each other. They should make sense to be near each other. But again, if you're doubling or tripling these E cell values, then you probably did a calculation wrong. Okay, so just double check your work. You might have forgotten the 0 somewhere, like right there. If you forgot that 0 out in front, I see that with some students often, is they forget that first 0. So just double check those calculations. Use your number sense to say, okay, these numbers are close to each other. Let's make sure that they make sense with each other. So let's look at this problem here. I want you to take a minute or so, pause your video, and I want you to look at, or to calculate E. This should be E cell. I forgot my cell. So this should be E cell. So non-standard E cell at 25 degrees Celsius, 298 Kelvin. For a galvanic cell based on the reaction below, where my cadmium ion is 0.072 molar and my magnesium ion concentration is 1.54 molar. Now I've done a little bit of the work for you. I've given you E cell for this reaction, okay? So what you need to figure out is the number of electrons. You need to figure out your N, how many electrons were transferred between those two half reactions. And then use that to calculate your E cell for non-standard conditions using the number of electrons and the 2 concentrations that we have for those solutions. So pause your video, take about a minute or 2 to try to solve this. You have your possible answers over there, and then check back with me so we can go through it together. Okay, so if you were to write out the 2 half reactions, you should get that, let's see, cadmium 2+ turns into cadmium solid. So we need 2 electrons on that side of the reaction to balance it. And then magnesium solid turns into magnesium 2+ and 2 electrons on that side. So N is going to be 2 because I have 2 electrons in each half reaction. So E cell is equal to our E cell naught, 1.97 volts. That's what we get from our E cell standard that was given to us, minus our 0.0257 divided by 2, ln of our products over our reactants. So that's going to be the magnesium over the cadmium. So let's see, the magnesium is 1.54 and the cadmium is 0.072. So let's do that in our calculators. Let's see. Natural log of 1.54 divided by 0.072. And then we multiply that by 0.0257 divided by 2, making sure those are in parentheses together. And then I'm going to do 1.97 minus my answer. And we get that E cell is equal to 1.93 volts. So you should have got an answer of C for that one there. So for our next problem, what I want us to do is to take this E cell at our non-standard conditions, and I want us to think one step further. So in class, we talked about our delta G, for E cell naught. So if we had E cell naught, we could calculate delta G. What I want us to now think about is, now that I have E cell at non-standard conditions, could I also calculate my delta G at non-standard conditions? We've looked at this a little bit before, way back in our thermodynamics chapter when we were talking about delta G. We also looked at it in your equilibrium chapter as well, when we talked about the difference between delta G naught and delta G itself. And we said that as long as we know the difference that delta G naught is for standard and delta G by itself is for non-standard, we can make that connection. And a lot of our equations were the same. So here, if we know our E cell non-standard and our delta G, okay, and we want to find, if we know one of those, we could find the other. But these are both for non-standard conditions, so this delta G is non-standard as well. So in our previous problem, we solved for E cell non-standard. So what I want us to do is use this equation that we found in our previous lesson, and I want you to calculate delta G at non-standard conditions. So take a second, pause your video, plug in your E cell at non-standard from our previous problem. Our Faraday constant that we can use here, let's say, is F is equal to 9.649 times 10 to the 4. That's our Faraday F. We already know the N from the previous problem as well. That was 2. So just plug in those values real quick and calculate your delta G. So it's important to note that our Faraday constant has units of joules per volt mole. Okay, so you got to remember that Faraday is in joules, and delta G is often shown in kilojoules. And I believe we showed these conversions again in our previous lesson, but we just got to remember that Faraday is in joules and delta G likes to be in kilojoules, so there may have to be an additional conversion. I personally like to leave that conversion to the very end and just do joules to kilojoules. If you wanted to convert your Faraday constant to kilojoules, you're more than welcome to do that. You're doing the same step as I am, just at the beginning rather than the end, whichever is most comfortable to you. So let's solve for delta G. Delta G for our non-standard condition is equal to -2 times our Faraday constant, 9.649 times 10 to the 4. Times our E cell at our non-standard condition, which from our last problem was 1.93 volts. So our Faraday constant is joules per volt mole. So that's just going to have our volts canceling. This 2 over here is technically a mole of electrons. So our moles end up canceling as well, and that's how we're left with joules. So if we put this into our calculator, we get -2 times 9.649 times 10 to the 4 times 1.93. And we get that delta G is -372,451.4, and that's in joules. We want our delta G's to be in kilojoules, so we're going to have to divide by 1,000. There's 1,000 joules in a kilojoule. So if I divide this by 1,000, oops, that's a 0. There we go. I get that delta G is -372.45 kilojoules. So that would lead us to answer B. Now this is a spontaneous reaction. Our redox reactions, in order to have spontaneous motion of anode to cathode, the electrons to move from anode to cathode spontaneously, we do need to have a delta G that is negative because that is our spontaneous value. So all of our delta G's that we should be seeing, at least in this case, should be negative to show that it's spontaneous. So we're always moving spontaneously in that forward direction from anode to cathode. So let's put it all together. Let's look at this problem from your homework. And it's asking us to do every bit of everything we've learned in our past few lessons, starting from standard potentials, even looking at half reactions. So everything from the beginning of this chapter until now. So what we're asked to do is to calculate E naught, so E cell naught standard, E cell non-standard, and delta G non-standard as well, for the reaction between magnesium solid and tin ions to create magnesium ion and tin solid. Our concentration of our solutions are given here. Magnesium ion is 0.025 and tin is 0.055. So what I want you to do is I want you to take some time, pause the video for as long as you need. You're going to have to write out the half reactions, figure out what's your anode, what's your cathode. You may need to refer to your standard reduction potentials for these half reactions in order to get those values for your anode and your cathode. Do your proper subtraction of cathode minus anode, and then use that to calculate E cell non-standard and your delta G at non-standard. Let's put that delta G equation back up here so you have it. Delta G non-standard is equal to negative NF E cell. Okay, so take a minute, pause your video for as long as you need, and solve all these different parts for this problem. Okay, I'm going to be moving around the screen a little bit here just to allow myself enough room for all the different parts that we need here. So I'm going to put my half reactions up in this top corner. So let's see, we first have magnesium solid going to magnesium ion. Oops, 2 plus, sorry. 2 plus. So I need 2 electrons here. And then we have tin 2 plus going to tin solid, so I need 2 electrons here. I've been using a lot of 2 electrons. A lot of these reactions are 2 electrons, so it's very common. So if we look at our standard reduction potentials for these reactions, let's see, I think the magnesium is negative 2.37 and the tin is negative 0.14. Our magnesium is going to be our oxidation because my electrons are on the product side, so that's going to be my anode. Oops. And then my tin is going to be my reduction because the electrons are on the reactant side, so this is going to be my cathode. So if I want to calculate E cell naught, I'm going to do cathode minus anode. So I'm going to do negative 0.14 minus negative 2.37. Remember, even though we are technically doing the oxidation is technically the reverse of the reaction we see in our standard reduction potentials, we ignore that change in sign. We ignore the fact that it's going backwards. It's not like delta H or anything like that like we've learned previously. It's not like that. We're accounting for the change in sign with our negative there, our subtraction. So we keep those signs as is. I like to keep it as a minus a negative just to remind myself that I do that. So let's see, negative 0.14 minus negative 2.37. And we get that E cell naught is a positive 2.23 volts. This should always be positive. Our E cell naught is always going to be positive for it to be spontaneous. So we have our E cell naught. So that answers the first question. Calculate E cell naught. Did that. Cool. Okay. Now we want to move over and calculate our E cell for our non-standard conditions at these specific concentrations. So E cell is equal to our E cell naught, that was that 2.23. And then we're going to subtract our 0.0257 over our number of electrons transferred. It was 2 electrons here and 2 electrons there, so our N is going to be 2, because it was 2 total electrons transferred from one reaction to the other. And then we're going to do the natural log of our products over our reactants. So the magnesium is 0.025, and then the tin was 0.055. So let's do that. Natural log, come on, nope. Natural log, there we go, 0.025 divided by 0.055. Okay, and then we're going to multiply that by 0.0257 divided by 2 in the parentheses. And then we're going to take 2.23 minus that answer. So we get that E cell is equal to 2.24 volts. And again, these numbers are very similar to each other. So we want to keep, that's a good way to check our work. They're very close, they're very similar, and that's where we would expect them to be. Okay, they shouldn't be off by 2 or 3 volts. So we did E at non-standard, so that's our second one. And now we need to calculate delta G at our non-standard conditions. Well, luckily we have all of the variables that we need for that already solved for. So delta G is equal to -2, that's our moles of electrons, times our Faraday constant, 9.649 times 10 to the 4. And then our E cell at non-standard, which was 2.24. So, -2 times 9.649 times 10 to the 4 times 2.24. And that's going to give us, let's see, delta G is equal to -432,275.2 and some change. And that's specifically in joules. It doesn't specify here what unit we need to be in because I didn't keep my answer boxes from our homework, but we can assume that if it's delta G, we're going to need it in kilojoules. So we're going to divide by 1,000 joules in 1 kilojoule to get our delta G at non-standard conditions to be -432 kilojoules. And we'll leave it there with 3 sig figs. Okay, our last problem that we have is in a separate video, so please just jump over to that video to finish up your note packet.